graphs and being able to recognize potential main effects and interactions in different kinds of graphs. So we're not talking about math stuff right now at all, though at the end we'll talk a tiny bit about that. But what you should get good at today is recognizing the characteristics of graphs that suggest main effects or interactions are present in the data. Okay? So we're going to start off with one experiment, really straightforward, kind of the simplest factorial design I can give you, which is 2 IVs and each one has 2 levels. Right? So it's kind of the smallest factorial experiment you can have. Because every IV has to have at least 2 levels, and we have to have at least 2 IVs. Right? So we've got, how many conditions do we have? How many different conditions do we have in this study? We've got 2 IVs, right? Each one has 2 levels. So what's our factorial notation? 2 by 2, right? So 2 by 2 design. Okay. And our first IV is beverage type. Half of our subjects are going to get a beverage that has alcohol in it. The other half are going to get a non-alcoholic beverage, okay, that smells like alcohol. Okay. So it's like a placebo. Right? Is that between or within?
It's a half between.
It's
a
half and half. Between, that's right. So this is between. All right? So we know we've got a 2 by 2. The first one is between. And we need to know whether it's a subject variable or manipulated variable. Manipulated, right? And with no other information, we'll assume that if it's a manipulated variable, I used random assignment. There's no reason to think I used anything else. Okay, so the first IV, between subjects, manipulated, random assignment. Okay. Next IV is expectation. Of the subjects in my study, half of the people are going to be assigned to the expecting alcohol group. So I'm going to tell half the people that you're going to get alcohol to drink. I'm going to tell the other half of the people that you're not getting alcohol to drink. And they're going to be randomly assigned to one of those 2 conditions. So is that between subjects or within subjects? Between. Is it manipulated variable or subject variable? Manipulated. Random assignment. Okay? So we've got 2 between subjects variables that are manipulated, and we used random assignment to put the people in the condition. So what kind of factorial design is this? A 2 by 2 what? It's a something factorial design. What is it? Random groups. This is a 2 by 2 random groups factorial design. Okay? Our dependent variable is the mean intensity of shock administered. Okay, so we're going to put people in these conditions. We have 4 conditions, right? 4 different conditions. There's people who got alcohol and thought they were getting alcohol, people who got alcohol and thought they weren't getting alcohol, people who didn't get alcohol but thought they're getting alcohol, and people who didn't think they were getting alcohol and didn't get alcohol. Okay? So we've got 4 different conditions, and in each condition we're going to look to see how intensely people in that condition choose to shock somebody else. Now, it's again not a real shock. We're just going to make them think they're shocking somebody else for making a mistake. Okay, a spelling mistake or whatever. So we're going to let people drink, and then we're going to look to see if it makes them mean drunks. Right? All right. So we've got our 2 by 2 random groups factorial design. Here is one possible outcome. Okay, here's a line graph. One possible outcome for this result. We've got beverage, first IV down here on the x-axis. We've got expectation, the second IV up here in the legend. And now I've graphed the data here in a line graph for you. And you can see that the no alcohol not expecting group dot is here. The alcohol beverage not expecting alcohol dot is there. The expecting alcohol but didn't get an alcoholic beverage square is there. And the expecting alcohol got an alcoholic beverage square is there. Okay? And we put lines in between them just to connect people who are in the same expectation group. Okay, so When we're looking at a line graph, if we want to know if there's a potential main effect of the variable on the x-axis, what do we look for? The slope, right? What's the slope of these lines right now? It's 0, right? It has a slope, but the slope is 0. Right? So these are not tilting in any meaningful way. That suggests, because these lines are flat, that there's no effect of whatever is down here on the x-axis. Okay, so this is no main effect of beverage. It did not matter whether people got a non-alcoholic beverage or an alcoholic beverage, they shocked the same amount. That's what that means. So there's no main effect of beverage type. Didn't matter. Now let's look at expectation. How do I tell? What do I look for when I'm trying to figure out if there's a main effect of the IV marked by the legend in a line graph? The distance between the two lines, right? Because what I want to know is, does it matter whether they were expecting alcohol or not expecting alcohol, how they behaved? And what do we see? They're basically the same, right? It doesn't matter. Didn't matter whether they thought they were getting alcohol or they thought they weren't getting alcohol. They still responded exactly the same. Those lines are right on top of each other. Made no difference, basically. Okay? So here we have no main effect of expectation either. Okay? So no main effect of beverage type, no main effect of expectation. Now, if I want to know if there's an interaction on a line graph, what do I look for? Crossing over. Do they have to cross over? What do they have to do? Move towards each other, right? They have to be moving towards each other and potentially cross over. They could cross over, but they don't have to. They just need to be moving towards each other. Are these lines moving towards each other? No. They are totally parallel. So, no interaction. So this is pretty much the boring graph of all boring graphs. We have no effect of IV1, no effect of IV2, and no interaction of IV1 and IV2. Boring. Okay? Unless, you want to find support for the null hypothesis, in which case, yay, it would totally work. Okay? Everything worked out great. Now let's look at that exact same set of data, but a different kind of graph. Okay, here's a bar graph. Same data, same numbers. Now I'm going to teach you a different set of cues to use. Okay? Same Y, same x-axis, same legend. Okay? Except now, the expecting alcohol is marked with black bars, and the not expecting alcohol is marked with white bars. So when you're looking at a bar graph, and you want to know if there is a main effect of the variable on the x-axis, what you want to do is compare the bars for each label. So you want to look at these two together and imagine them together, and compare it to these two together and imagine them together. Okay? So imagine if I smush those together into one lump, smush these together into one lump. Would they look the same or different? They look the same, right? So these bars together compared to these bars together, no difference, means no effect of this variable. So the bars on the left compared to the bars on the right. Okay? They look exactly the same. So no effect of that variable. Right? All that means is it doesn't matter whether they got a non-alcoholic drink or an alcoholic drink, they behave the same way. Right, now for the variable up in the legend, you'll see the levels of this variable are marked with one level has a black bar, one level has a white bar. So if you want to know if there's a main effect of this variable, now you're going to compare the black bars and the white bars. So now I'm going to compare these two bars smushed together with these two bars smushed together. Do they look really different? Now, black bar is a little bit taller, but not very much. Probably not enough to matter. I mean, numerically different, but probably not enough to matter. The chances that there's a difference between the black bars and the white bars is pretty small. So no effect here of expectation. If I look at the black bars together and the white bars together, we're pretty much talking about the same size of bar. Now, for the interaction, if I want to see an interaction on a bar graph, what I'm going to do is look at pairs of bars. We'll start over here on the left. Here's what I see. I see a pair of bars, and the black bar is a little bit taller than the white bar. Now I'm going to take that pattern, and I'm going to look to see if it holds for the next set of bars. Over here. Oh, look. Black bar is a little bit taller than the white bar. When we're doing the interaction, what we're looking for is the difference and the direction. Okay? In both cases, we have the same difference, this much, and the direction is the same. It's the black bar taller than the white bar. The fact that the patterns match in difference and direction means we have no interaction. The fact that the pattern matches in difference and direction means we don't have an interaction. All right, let's do it again. We're going to go through every possible combination for this study until you guys can do this in your sleep. Once more with feeling. Main effect of the variable on the x-axis. How do I tell? Line graph. How do I tell if there's a main effect of the variable on the x-axis? The slope. Okay? We want it to be something not 0. Look at those lines. What's their slope?
0.
0. So do we have a main effect of the variable on the x-axis? Nope. Again, it makes no difference whether they got a non-alcoholic beverage or an alcoholic beverage. The amount they shocked was the same. Okay, let's take a look at the variable up in the legend. How do I tell if there's a main effect of what's up in the legend? Distance between the lines. Okay, now take a look. Compare this to the one we just did. The first one. What do you think now? Do you think we might have a main effect? Does it matter whether they were expecting alcohol or not expecting alcohol? Yeah, it sure does. People who were expecting alcohol shocked a much higher degree than people who weren't expecting alcohol. So here people are like, I'm getting drunk, I can be mean, and I can blame it on the alcohol. It's not my fault. You got me drunk. I'm not responsible for my actions if I'm drinking. It's the beer talking, honey. Right? That totally lame excuse. Come on, baby, it's just the beer talking. Don't take it personally. Moron. Okay, so definitely it matters. We've got a main effect of alcohol, of expectation, such that people who were expecting alcohol shocked more than people who weren't expecting alcohol. And you just described the result, a main effect of expectation, such that people who were expecting alcohol shocked with a higher intensity than people who weren't expecting alcohol. Right? Interaction. How do I tell if there's an interaction in a line graph? If they're moving towards each other or if they actually cross. Is there any possibility those two lines are moving towards each other? They are not moving towards each other. They are not going to cross in any space or time that I'm aware of. There is no interaction here. Okay, so this graph shows only a main effect of expectation. That's it. I'm going to show you a bar graph with the exact same pattern. And here's what that would look like if we did it as a bar graph. So, x-axis. We tell whether there's a main effect of what's on the x-axis by comparing the bars for each category. Down here. Okay? So I've got non-alcoholic category and alcoholic category. If I look at these bars together and compare them to these bars together, do they look the same or different? Same. So since they look the same, we're talking about no main effect of beverage. It didn't matter whether the people got a non-alcoholic beverage or an alcoholic beverage, their behavior was the same. Now, expectation. People who were expecting alcohol are represented, their amount of shock was marked with black bars. People who were not expecting alcohol are marked with white bars. What do you think? If I compare the black bars to the white bars, they look different?
Yes.
Yeah, they totally look different. The black bars are twice as high. So again, people who thought they were getting alcohol were happy, happy, shocky, shocky. And the people who were expecting alcohol, just kind of exact same pattern of results, just presented a different way. Interaction for a bar graph is looking at the pattern of results for a set of bars and then comparing it across the graph. Right? And we're looking for difference and direction. So here, I've got the difference. The difference is this much, with black taller than what? Move over here. Same difference, same direction, black taller than white. Okay? Same difference, same direction means no interaction. There's no interaction of these two things.
Can you say that one more time?
Sure. Which part?
Same.
Same direction, same direction, same difference. Okay? Same difference, same direction. So, no interaction. So all we see on this graph is that main effective expectation, such that people who were expecting alcohol shocked the other person significantly more than people who weren't expecting alcohol. Okay? Make sense? Can you see that on the graph? Okay. Lines, more lines. We're just going back and forth. Mental flexibility is key for this. All right. So, how do I tell? Got a line graph. How do I tell if there is a main effect of beverage? Slope. You want a slope that's not zero. How's the slope of these lines looking? Is it looking very zero-y?
No.
No, it's looking really steep. Right? So what do you think? Does it matter whether someone got a non-alcoholic beverage or an alcoholic beverage? Yeah, it really matters. People who got an alcoholic beverage shocked significantly more than people who got a non-alcoholic beverage. So there's a main effect of beverage such that people who got an alcoholic beverage administered a significantly higher shock than people who got a non-alcoholic beverage. Can you see that in the graph? Now, what about expectation? Expectation. People who were expecting alcohol are the solid line. People who were not expecting alcohol were the dashed line. Do you think we have a main effective expectation in this graph? Okay, people are saying no. Why not? Because the lines are really close together. They're not that different from each other, right? The people who were expecting alcohol are here. The people who were not expecting alcohol are here. They're right on top of each other. So they're basically doing exactly the same shock. So no main effect of expectation in this graph. Okay, is there an interaction of beverage and expectation?
No.
Have a vote for no. Why not?
Because they're parallel.
These lines are totally parallel. There's no way they will ever intersect in any space and time. They're not even moving towards each other at all. So parallel lines mean no interaction. All right. Same data, different kind of graph. Okay? Exactly the same pattern. So, what I'm trying to tell if there is a main effect of the variable on the x-axis, and I'm using a bar graph, what do? Someone tell me what I need to compare to know whether it matters if they had a non-alcoholic beverage and an alcoholic beverage. What do I need to do?
Compare the pattern.
No, not patterns yet. Patterns will say for interactions. What am I comparing? What bars am I comparing to what bars?
Black and white.
We're comparing this pair of bars to this pair of bars. Do they look the same? No. They don't look the same at all. We got little short stubby bars over here. We've got tall strapping grown-up bars over here. So there's a main effective beverage such that people who drank an alcoholic beverage shocked significantly more than people who had a non-alcoholic beverage. Can you see that on the graph? That effect? What about effect of expectation? What am I going to look at? What am I going to compare? Which bars am I going to compare if I want to figure out if there's an effect of expectation?
The black and white.
Going to compare the black bars together to the white bars together. So if I'm going to compare the black bars together to the white bars together. So what do you think? If I smush the black bars together and compare them to the smushed white bars together, is it very different?
No.
No. This is the same thing as the lines being close together. So, no main effective expectation. All right, what about interaction? Okay, when it comes to interaction, we're interested in the pattern. This is Abby's one, the pattern. Okay? And the pattern has to do with difference and direction. So, this might not seem super intuitive right now, but let me show you. All right, so here, black is this much taller than white. So the difference is this much, and the direction is black taller than white. Right? Now I'm going to come over here. Even though it's a lot higher, that doesn't matter. What's important here is that it's still black this much taller than white. Okay? It's still this much difference, and the direction is still the same. That tells me, since it's the same difference, same direction, that there's no interaction. Okay? If it's same difference, same direction, no interaction. So it does not matter that these bars are short and those bars are tall, because we don't care about anything below the top. All we're interested in is how much taller is the black bar than the white bar, and are they going the same direction, with the black bar being taller than the white bar. Difference and direction. So, main effect of beverage, no effect of expectation, no interaction. Okay. Getting fancy now. So, do we have a main effect of beverage?
Yes.
Probably. Why?
There's a slope.
Slope is not zero, right? The lines are slanting. Okay? What is that main effect? There's a potential main effect of beverage such that, what? Describe it to me.
People who got alcoholic beverages shocked more than people who didn't.
Right. So people who got alcoholic beverages shocked significantly more than those who got non-alcoholic beverages. Can you see that on the graph? Okay, what about expectation? Do we have a potential main effect of expectation?
Yes.
Okay, how do you know?
The distance between the lines.
Because the lines aren't right on top of each other. There's some distance between them. Okay, so what's the main effect of expectation then? There's a possible main effect of expectation such that who shocked more than who? People who were expecting alcohol shocked others significantly more than people who were not expecting alcohol. So if they thought they were going to get some alcohol, then they were shocking people more. Again, that's the, well, I can blame the alcohol, I'm not responsible for my actions. Okay. This one down here is, I am drunk, so that's why I'm doing this. Okay. Interaction.
No.
How do you know?
They're parallel.
The lines are parallel. Okay. See, you're getting faster at this. Practice makes perfect. Okay, bar graph. Same data. Now in a bar graph. So we said last time, 2 main effects, no interaction. How do I know that on this graph? How do I know that there's a main effect of beverage? Main effect of beverage. Compare the pairs. Okay, there's all kinds of pairs. What pair? Beverage. I'm doing beverage, so I'm comparing the non-alcoholic bars to the alcoholic bars. Do they look the same? No. These bars are a lot shorter. Okay, bars for non-alcoholic are a lot shorter than the bars for alcoholic. So same pattern, right? People who got an alcoholic beverage shocked significantly more than people who got a non-alcoholic beverage. You can see that in the graph. What about expectation? We said before there's a main effect of expectation. How do I know that? Looking at this graph.
You combine the blacks, combine the whites, and compare that.
Okay, so combine the black bars and then combine the white bars and compare the combined bars to each other, right? So the black bars together and the white bars together, and what am I going to find?
There's a difference.
The black bars are
Bigger.
Okay? Black bars are the expecting alcohol, right? So that means people who were expecting alcohol shocked more than people who weren't expecting alcohol. Right? Same story. Different graph. All right? Interaction. We said before, there's no interaction. It's easy to see with parallel lines. How do I see that in this graph? It's the difference and direction when I compare the patterns. So here I have black is this much taller than white. When I come over here, same difference, same direction, no interaction. Okay? Same difference, same direction, no interaction. Oh my gosh. All right. Now the rules change. Because in the absence of an interaction, we can pay attention to main effects, right? So remember what I told you last time. The presence of an interaction skews the cues you use to tell if there are main effects, right? Interactions skew the cues. We can see that. Do you think there might be an interaction here?
Yes.
Yeah, because the lines are moving towards each other now. Okay, not parallel anymore. So first thing I want to say is it looks like there's an interaction here. We take a look at this graph and we see that there's an interaction. Is there any one particular condition that seems to stand out? That seems to be more different? So this is about 30, this is about 40, this is about 50, and then this one is 100.
The expecting is
This up here is expecting alcohol and got alcohol. So these are the drunk people who were expecting to get drunk. But that's the interaction. That's beverage and expectation coming together. When you think you're going to get drunk and you do, you are free of personal responsibility. Why do you think people go out drinking with the intention of getting drunk? They want an excuse to let their hair down and shock strangers for making spelling mistakes. All right, so, or, whatever. But when someone's all wound up like, I need to go drink and just let off some steam, right? But they're saying, I intend to go out and get drunk, and when I do, then I'll be able to do things I wouldn't otherwise do. Right there. It's science. Okay? So when we talk about the interaction, we'd say there's an interaction of beverage and expectation such that, and now because we're talking about an interaction, we've got to talk about both IVs together. Participants who got an alcoholic beverage and were expecting an alcoholic beverage shocked others significantly more than people in the other conditions. That's the easiest way to do it. Find the condition that pops out, that stands out to you, and describe that condition. And that makes sense, right? If you think you're going to drink and get drunk, and you do get drunk, then you kind of, you can mentally prepare for what you're going to do then, right? You're okay with it. You think you're getting drunk, you are getting drunk, inhibition is released, and party, or shock. Whatever, same thing, shocking, partying. All right, it's release of personal responsibility. All right, now, main effects. I told you, in the presence of an interaction, it skews the cues you use. You have to worry about that. Say that 10 times fast when you're drunk, and it's tough. All right, so if we look at this axis, we're talking about slope, right, for the main effect. But you'll see the slope here is very slight. The slope here is more extreme. So it's possible we have a main effect. You have to kind of think of the average of those two together, those two lines together. It's possible we have a main effect. But again, the cue is kind of slanted. It could be artificially enhanced by the presence of the interaction. So yes, it looks like there could be a main effect. These lines are not flat. There could be a main effect of beverage, but we have to take it with a grain of salt. Must be tequila. Okay. But take it with a grain of salt because that interaction is present, and interactions have the ability to exaggerate or suppress main effects in the data. So, looks like we could have one, but we want to not get too excited about it. We're more interested in the fact that we observed that interaction. Now, when it comes to expectation, what cue do we use to decide if there's a main effect of that variable? How close the lines are to each other, right? If they're far apart, we think there's a main effect. If they're close together, we think there's not. Okay, what do I do here? Close together, far apart, right? So you have to think about kind of on average how far apart are they from each other. And they're not like right on top of each other, so we can say, yeah, okay, there may be a main effect of alcohol, but again, the cue is skewed because of the presence of the interaction. It's not a consistent cue anymore. It's being influenced by that interaction, so we want to be a little bit less confident in what that means. We can say that there is a potential main effect. The math might even show us that there's a statistically significant main effect. But in a paper or whatever, we don't get too super excited about those main effects because we know that they could be artificially enhanced by the interaction. All right. Now, let's take a look at this same thing, two main effects and an interaction in a bar graph. And you'll see, yeah?
So do we say there could possibly be a main effect?
Yeah, sure. You can say that there's a possible main effect of expectation, there's a possible main effect of beverage, just to show that you recognize we're a little bit less confident because the interaction is present. Since you don't actually have the math to give you an answer. Okay, now here it is in a bar graph. And for me, seeing this in a bar graph, this interaction is a lot easier. So, remember, interactions in bar graphs aren't about lines coming together. They're about difference and direction, right? Okay, so I want to show you now what this looks like when you do have an interaction. Okay, difference and direction. Black is taller than white by this much. Okay. Difference and direction. Well, the direction is the same. Black is still taller, but the difference is a lot more. That tells me I've got an interaction. Okay. Same direction, but very different difference between the two. So in order to have an interaction, or let me back up. In order to say that there's no interaction, these need to match for the comparison. When you compare the patterns, they need to match. If they both don't match, then you probably have an interaction. If the difference isn't the same between the two bars, or the direction of the difference isn't the same, then you've got an interaction. That's the rule we're going to use. And here we see a difference that's about this much, and when I come over here, the difference is clearly substantially larger in this case. So we say interaction. And it's much easier to me to see that standout bar, because look how much different this bar looks than the other ones. So if you get a graph like this, and I ask you to just tell me, is there an interaction, and if so, describe it to me, you can say, yes, there's an interaction. I can tell because this pattern is, this difference is so much more than this difference, even though the direction is the same. And if I had to describe that, I would say that there is an interaction of beverage and expectation such that participants who got an alcoholic beverage and were expecting alcohol administered the highest shocks. This is why we just put up pictures, because it's a lot easier than saying all that. Right? But you have to know how to turn the words that you know into the right picture. Right? And you have to know how to read that picture. All right, now we'll talk about main effects. Main effect of beverage would be comparing these bars to these bars. Do they look really similar? No. So you say, yeah, there's probably a main effect there. Because I think these bars together are a lot bigger than these bars together. So main effect, people who got alcoholic beverage were more, administered a higher shock than people who got a non-alcoholic beverage. If I want to do this one, expectation, it's comparing black bars to white bars. Okay, if I compare black bars to white bars are going to be a lot bigger, right? Overall. So again, if you are expecting alcohol, you administered a significantly higher shock than if you were not expecting alcohol. But because we think there's an interaction here, you might want to counter that. Let's say there probably, or there may be, there's possibly a main effect here. If there is a main effect, we have to be cautious in interpreting it because of the presence of the interaction. Okay. What about this one? What just jumps out at you?
Everything.
Everything. The interaction, right? This is all interaction all the time, no main effects. All interaction all the time. So we definitely have an interaction here. This is called a crossover effect. And, but we do not have any main effects. The interaction is easy to see, right? I mean, the lines literally do intersect. They interact with each other, right there, right in the middle. Right? So we've got an interaction. Who shocked the most? Okay. Well, now we don't really have one that's standing out. These are both really high shocks. So who are these people? And what do they have in common? How can we describe this? All right, so these people were not expecting alcohol, right? Because there's a circle. Not expecting alcohol, and they didn't get it. And these people were expecting alcohol, and they got it. So what do those people have in common? They got what they were expecting, right? So participants who got the beverage they were expecting administered significantly higher shocks than people who got a beverage that they weren't expecting. I don't know why that would be true, but that's what that graph says. So if people were expecting alcohol and they didn't get it, or if they were expecting non-alcohol and they got alcohol, they shocked less. So people who got the beverage they were expecting shocked the target significantly more than people who got the beverage they weren't expecting. That's what happened here. Now let's think about the main effects. Okay, if I'm doing the main effect here, on the x-axis, what do I look for in a line graph? Slope. Okay, here's the problem. Here's how I know there's no main effect here. Because the slope of this is exactly the opposite of the slope of that. What happens when I look at those two slopes together? They cancel each other out. So no effect. The slopes cancel each other out. There's no main effect. When the lines go in the opposite direction like this, there's no main effect. They've canceled each other out. Yeah?
What if they just have different slopes? Like, this is kind of an X shape. What if it was more like a...
Then it's possible you could get a main effect. But when you get these crossover effects, the interaction is very powerful and tends to suppress main effects. So the main effect, again, is possible, but it's more likely to be weak.
Okay.
If we think about the x-axis, this legend variable, we look about how far apart are the lines from each other, right? Well, what does that mean? So here they're far apart, here they're together, how far apart are they? They're not far apart at all. They're right on top of each other. So, they're literally like where one is high, one like it's high and low and high and low. There's no difference. So, no main effect. When you see this kind of thing, this is no main effect, no interaction. Now, let me show you what this looks like. Excuse me, there's an interaction but no main effect of either variable. Let's take a look at this in a bar graph. Alright, so here, this makes it actually a little bit easier to see the fact that there's no main effects. If I think of these two together and compare it to these two together, no difference, right? If I combine the non-alcoholic bars together and compare it to the combination of the alcoholic bars, no difference. Think about what's up here on the on the legend. Compare the average of the black bars to the average of the white bars. No difference, right? Now the interaction here comes now not in the difference, but in the direction. Okay? Here I have black shorter than white by this much. And over here it's the same difference, but now the direction is different. Now it's white shorter than black. So last time when we had the first interaction I showed you, the difference varied, but the direction was the same. In this one, the difference is the same, but the direction has switched. So if they don't match in difference, or they don't match in direction, or both, right? They don't match in difference or direction, you've got an interaction. And people always goof this up on tests. I show them this picture, and I ask if there's an interaction. And they say no. Then I say, tell me whether or not there's an interaction, and tell me how you know. And they say, there's no interaction because the distance between the bars on the left is the same as the distance between the bars on the right. And I go, yeah, except that the distance is going different directions. In this side, the people who were not expecting alcohol behaved a certain way, and here, the people who were expecting alcohol behaved a certain way. Here, it's the people who who got no alcohol and weren't expecting it, who shocked a lot. And over here, it was the people who got an alcoholic beverage and were expecting it that shocked a lot. There's a difference. What they have in common is that they got what they thought they were going to get. Their expectations were met. And the people whose expectations weren't met maybe were like, wait, what's going on? I thought I was supposed to be drinking vodka here and I'm feeling totally fine. Oh, I bet this is the truth. Right? They're telling me I'm drinking, but I'm not really drinking. Okay, I'm drinking, cool. Then you got other people who were expecting not to get any alcohol, and all of a sudden they're starting to feel kind of buzzed and like, whoa, I had no clue I was that much of a lightweight. I'm drinking water that smells like alcohol and I'm buzzing. Whoa. Okay, just play cool, it's good. Don't act, don't think I'm a total baby or anything. And so they're like being more mellow. Or something like that, right? You've got to explain it somehow, but that's what the data said. Alright. Now, let's switch it up a little bit. Gonna go crazy. Add another level. Now, instead of just being drunk or not drunk, we're going to use a legal limit. So we're going to have people who are either legally drunk with a blood alcohol level of 0.1, people who are legally impaired with a blood alcohol of 0.05 but are not officially drunk, and people who are sober. Okay, so 3 levels of blood alcohol content. And then our second IV is going to stay the same with expectation. Also, dependent variable is going to stay the same. So now I have a 3x2 random groups factorial design. 3x2 random groups factorial design. 6 different conditions now instead of 4. All right, so this pretty much looks the same. You can interpret this graph exactly the same way we did before. Do we have a main effect of blood alcohol content? Why do you think so? Because the lines are not flat. The lines are moving in the slope away from the x-axis. Yep. Okay. What about, do we have a main effect of expectation?
Yes.
Yeah, probably. Why do you think so? Because the lines are not right on top of each other, they're far apart. Do we have an interaction? No. No interaction. Because
Parallel.
the lines are parallel. Here's what that looks like in a bar graph. So we said before that we thought we had a main effect of beverage and a main effect of expectation and no interaction. All right. So, main effect of blood alcohol content. What am I going to do? I'm going to compare these bars together with these bars together and with these bars together. So I'm looking at all 3. I've got 6 conditions now. I've got even more opportunities for things to be different, right? You start throwing in more conditions, there's more chances for something to happen. So, does this pattern look different from this pattern, look different from this pattern? Look how short these bars are. Look how tall those bars are. Remember, we're talking about these bars together. Okay? Like if I take the average of these 2 bars and compare it to the average of these 2 bars and compare that to the average of those 2 bars. Yeah, they're different. That's that main effect of blood alcohol content. And the main effect is that people who had higher blood alcohol content administered a significantly higher shock than people who had lower blood alcohol content, right? People, and chances are, actually, we did all the Tukey tests we needed to do, we would find out that people who were legally drunk administered a higher shock than people who were impaired and people who were sober, and people who were impaired administered a higher shock than people who were sober. Something like that. Now, what about expectation? What am I comparing?
The black.
The black bars all together with the white bars all together. They look different, you think? The black bars are always taller, right? That's the main effect of expectation. So people who expected alcohol administered higher shocks across the board than people who were not expecting alcohol. Now, interaction. Interaction has to do with difference and direction. Okay? So my difference is this far and black is taller than white. This far, black is taller than white. This far, black is taller than white. Same difference, same direction, no interaction. Sorry, see he's doing the hand motions now too. Same difference, same direction, no interaction. No. I won't do it the Japanese way because that'd be really confusing, because to say no in Japanese you go like this. That way looks like interaction. So. This is good, this is bad. You don't go like this in Japanese, that means you're going to give somebody money. Okay. Ooh. Now things are getting complicated. What do you think? Probably an interaction going on now. Now it seems to matter, combinations of things seem to matter now. Because that's what interactions are about, right? Combinations of conditions are special. Blood alcohol content and expectation are starting to interact with each other and result in something unique under certain circumstances. So there's an interaction, it looks like, between expectation and blood alcohol content such that what? Do you see a standout condition in there that you might be able to describe? Which condition has the highest shock? Expecting alcohol and legally drunk. So participants who were legally drunk and expecting alcohol administered significantly higher shocks than participants in the other conditions. Would you agree? You should agree, because I'm right. Now, what we don't know, because we don't have a little test, it could be that these are also significantly more than this. We don't know. We'd have to do all the math. But you can look at that graph, and if someone put a graph up like that and said, what we see here is that people who were legally drunk and who were expecting an alcoholic beverage were significantly more aggressive than people in the other conditions. You should know why they just said that. Because you can see that these folks are feeling shocktastic compared to these folks. They're really different from everybody else. Now, let's look at that in a bar graph, and you'll see that it pops a little bit more. You can see the interaction here, for sure, I hope. So difference in direction, black taller than white. Come over here. Oh wait, black taller than white, but the difference has changed a lot. Get over here, black taller than white, and the difference has changed even more. So definitely interaction. We've got an interaction of these two things. And the tallest bar on that graph is this one right here. So that's the one that you're probably going to focus on. That's the combination of those two variables that's doing the most interesting thing. Drunk people who are expecting to get drunk are the most aggressive. Okay. Now let's look at, oh gosh, now things are getting a mess. What's wrong with this?
It's half and half.
It's like half and half. We start here, so your first thing you look at and you go, well, they're not parallel. At least partially. But this is definitely an interaction. They are not parallel. This is definitely an interaction. This is what we call a dose-specific effect. Okay, a dose-specific effect. And basically, this is why the law is written the way it is. That it's considered a bigger deal to drive drunk than it is to drive impaired. Okay, to be intoxicated is worse than being impaired, because people who are impaired are, yes, they're impaired relative to people who are sober, but the difference is not so much. They still represent a potential danger, but they're not as dangerous as people who are actually drunk. Okay, and we call this dose specific because in order for the interaction to appear, you have to have a particular dosage. In other words, you have to have enough alcohol for the effect to show up. Before people get really aggressive, they have to hit that criterion of being legally drunk. Below that criterion, they're not going to show the effect. So they might have alcohol in their system, but they're not going to get violent yet. It's when they hit that drunk level that all of a sudden they're likely to display the effect. That's why we call it a dose-specific effect. And this is true with all kinds of medications. With a little bit of medication, you're fine. A lot of medication, you have a bad reaction, right? That's why they might have to figure out, when you're taking a medication, how much is good for you based on your weight and your height and your age and other stuff like that. Because it might vary for you, and what's going to give you a good effect could be different than what gives you a bad effect. And that's what we're seeing here, is this dose-specific effect. The interaction only occurs after a certain dosage is reached. It's not a linear effect. It's a dose-specific effect. We get no interaction, we get no interaction at lower dosages of alcohol, but then at the higher dosage, the interaction emerges. Okay, so we would still say there's an interaction here, but we would also qualify it as a dose-specific effect that only emerges at the highest dosage of alcohol. No interaction at lower dosage levels, and interaction at the higher dosage levels. Does that make sense? Here's what that looks like in a bar graph. And here's where you can really see the dose-specific. Here's how that lays out here. Notice difference in direction that much, black taller than white. Same pattern, black taller than white, so no interaction yet. But when we get to this end, definitely interaction. Boom. Same direction, but substantially larger difference between the two bars. So this would be a dose-specific effect in a bar graph. And when you get those, the interaction is definitely the most interesting thing. Because dose-specific interactions mean that effects could be hiding, right? Like you might actually get a significant effect at higher dosages for other things. That's why when we test medications and alcohol and stuff like that, they're really interested in what dose will give the desired effect and what happens if you get too much. Okay. So now we're going to talk a little bit about math. We're going to do it in the context of a real experiment describing a real psychological phenomenon. So this experiment, people were assigned to one of three levels of arousal. And here, arousal refers to level of alertness. This isn't sexual arousal. I mean, it could be, but that's not what they're talking about. Here they're talking about whether you're like really excited, amped up, alert, high level of that, versus kind of a medium level of alertness, versus a low level of alertness. So high, medium, and low arousal. And then task difficulty. So they can either do an easy task or a hard task. And what we're assessing is people's performance on the task. So we're curious if there's an interaction between how alert people are and how hard the task is they have to do. So another way to think about this. This is, I drank a 6-pack of Red Bull. This is, I had a Coke. This is, I had warm milk. This is 35-30 final with no note card. And this is intro final open book. Okay? You can handle that. Over one chapter. Okay. All right, just to give you some context. All right, so now you have a sense of... And this is what really happens. Okay, we see a dose-specific effect. That when people are at a low level of arousal, and it doesn't really matter whether their performance is okay, we do see that when the task is difficult, they do worse than when the task is easy. That makes sense, right? Low level arousal. Okay, I mean, if you're pretty relaxed and you have to do something easy, fine. You're going to do better at it than something that's a little bit harder. Okay? Because the task is hard. Hard things are supposed to be harder, right? You're supposed to do worse on them. That's why they're harder, because you're less likely to do well on them. Right? All right. So then at the middle level, as people get more alert, their performance gets better. Right? When you're alert and paying attention, you get better at doing both easy and hard things. Okay? So moderate level of alertness is good for performance on both easy and hard tasks. Moderate level of alertness. But when you get to super high levels of alertness, okay, if you are flying on 5 Adderall, right, or that 6-pack of Red Bull plus a couple Monster Chasers or something like that, because you're like, this is really important, I gotta get a really good grade on this. I've been studying its finals week. I'm so tired. So you like just do, and you know people like this. Right? They're like, I'm just going to totally bust out the caffeine. You know, they're popping caffeine pills and drinking Red Bull, and walking around looking like that. I see them every finals week. I'm just, why do I want them to relax? Because here's what happens. Their performance on hard tasks crashes. When you are too amped up, you can't concentrate on hard tasks. And your performance actually drops to as if you were not alert at all. Your performance on easy tasks goes up because you are so aware and it's easy. Okay, so it continues to go up. But we see a really clear difference in how people respond to easy tasks and difficult tasks. Okay? Yes, it's true that the more alert you are, the better you do when you're doing something easy. But when you're doing something hard, you actually get an interaction where it becomes harder to do difficult tasks when you are too stimulated. So what's the message for this class? The message is, first of all, don't take your roommate's Adderall before the final. Don't drink a 6-pack of Red Bull. You want to have a moderate level of alertness because the final will be challenging. It's a cumulative final for a challenging class. We're okay with that. Difficult is okay. But you want to maximize your potential for doing well, so you want a moderate level of alertness. Being a little bit nervous is okay. Freaking out is not going to help you. Okay? So you want to be adequately prepared, adequately rested, a little bit nervous, maybe a good cup of coffee with an extra shot of espresso, that's fine. But do not amp yourself through the ceiling for that test, because you'll be here, not here, and that's where you want to be. Okay? All right. So now let's take a look at the data. This is a source table for that graph, okay, for that dose-dependent effect. Now, this should look familiar. What up here do you recognize? Between conditions, within conditions, that should look familiar, right? So, what's this number right here? The sum of squares between conditions. And what's this? Degrees of freedom between conditions. And what's this? The sum of squares within conditions. And what's this? Sum of squares total. And it is the sum of it's like being the weather guy, right? I'm not looking. It's right here. Somewhere. All right. But you see, so this looks familiar? Vaguely familiar? Okay. Now, a couple things I want you to notice about this chart. There is no mean square between conditions. Okay, do you see that? It's not. I didn't forget it. We don't put it on there. That's the first thing I want you to notice. So if I show you a chart like this, don't calculate mean square between conditions. It's not there because you don't need it. What you do have is the mean square for IV1, the mean square for IV2, and the mean square for the interaction of IV1 and IV2. Do you see that? The mean square for the interaction. So here's a mean square for IV1, which is level of arousal. Mean square for IV2, which is task difficulty. And the mean square for the interaction of arousal times difficulty. Okay, you see that? All right, now I'm going to tell you. What we've done here, we've got two between subjects variables with random assignment, manipulated variables. So this is, we've got, think about these conditions. Go back and take a look. We've got a 3x2 random groups factorial design. Okay. And from this table, you can calculate F observed for each of the main effects and for the interaction. And you can look up the critical value. Let me show you how you do that. Remember, think of this like kind of a really fancy independent groups ANOVA, or between subjects one-way ANOVA. Okay? If you were doing a one-way ANOVA between subjects, how would you calculate F observed? For between subjects. How do you calculate F observed? For one-way ANOVA, you just did a test. One-way ANOVA, how do you do F observed? MS BC over MS. Right? Remember? It's in there somewhere. You're like, that was puffed bread. Do you know how many beverages of various types I've accessed there? I'm not even sure I have all those brain cells anymore. It was a good break. Okay, but that's what we would do, right? And we would look up, if we wanted to look up F critical, we'd use degrees of freedom between conditions and degrees of freedom within conditions, right? So look it up. This would be numerator, and this would be denominator, right? Are you with me so far? Nothing too crazy. All right. So if we want to do the F observed for the main effect of level of arousal, what do you think we're going to use? There's nothing here, so that can't be the answer. What would make sense? If I was going to do the main effect for level of arousal, what would I do? Brandon?
You would do degrees of freedom of...
I'm calculating observed, so no degrees of freedom.
Oh, you do mean square of arousal...
So this one.
No.
That's the mean square of arousal.
Arousal times the interaction.
Okay, that's the interaction down here, okay? So remember I told you before, when we do factorial designs, we have to do an F test for the main effect of IV1, an F test for the main effect of IV2, and an F test for the interaction. Okay? So there's actually enough information here to do 3 different F tests and look up 3 different F criticals. Okay. To do the F observed for IV1, we would do this. That's all. That's it. So it would be 30 over 5. F observed for the main effect of level of arousal is 6. Done. 30 divided by 5 is 6. That's F observed for level of arousal. To look up the critical value to compare that to, I'm going to use degrees of freedom for the level of arousal, and this one, and within conditions. So it's going to be 2 and 24. Okay? All I'm doing Exactly what we did for one-way ANOVA. Now I just have enough data to do it 3 times. All right, let's see if you got the pattern. I want to calculate F observed for the main effective task difficulty. What am I going to use in my formula for the main effective task difficulty for F observed?
120.
Yeah. All I'm going to do is switch that out. Ta-da! So now it's 120 over 5 will give me F observed. And what degrees of freedom am I going to use to look up the critical value? 1 and 24. Yep. And what about the interaction? How am I going to do the calculation for F observed for the interaction? What's going to go in my numerator?
30.
Okay, the main effect, the mean squared for the interaction, which is right here. Over 5. And what am I going to use for degrees of freedom? This degrees of freedom is my numerator. That one's my denominator. So I won't ever make you generate a table like this, but I do expect you to be able to use one to calculate F observed and to identify appropriate value of F critical. And with this information, you could also do eta squared for each one of those. You can figure out effect size.